So welcome back guys. This is a major part. So lecture 5, the design of lead compensator by using Bode plot. So we have followed some so I just speak about the previous lecture. So we just involved in region 1 and region 2. So based upon the procedures I'm teaching that. So you will be giving open loop transfer function. So G of S. Okay. So some function g of s. Now in step 1, what we'll do is the open loop gain k of this given system is determined to satisfy the requirement of error constants. Okay, in region 1 we'll find the error constants, right? Kp, kv, ka. So for this transfer function they will be given a ka value, kp value or kv value. So based upon the kv, kp, ka, we'll find the k value for the system. Okay. So that means if a system is g of s is given as k by some s plus s into s plus a, like that. So this k value will be found by using this kp, kv, kv. That means they are giving indirectly the system overall response of steady state error. Okay. So in first case only we are satisfying the steady state error. Okay. So later part we'll move that. Okay. After getting this k value with this system, we'll draw the Bode plot is drawn for the uncompensated system using the value of k. Okay. So if we incorporate k value, we using this system, we draw the Bode plot. After plotting the Bode plot, after getting the Bode plot, we'll find, so we'll do that all this stuff, magnitude plot and phase plot, and we'll find phase margin phi for the uncompensated system. Okay, so if the specifications already said that specifications will be phase margin, gain, cos or frequency, kp, ka, kv, these are the specifications. This thing is met, but phase is not met. Okay, the phase margin will not met. If phase margin is met, the design is complete up to here. Okay, so that means if my specifications is given as phase margin and omega gc and ka, kp, kv, let us example. So first of all at region 1 we'll find with that kv value we'll find ka and design the Bode plot, and we'll find phase margin for that Bode plot. If that phase margin is equal to this phase, that is desired phase, then my design is completed with k only. That means proportional is enough, p is enough. Okay, but it does not match. So if does not match with this phase margin, then we have to go to step 4. That is, in step 4 we have to determine the maximum phase angle controlled by the lead angle. So as I said previous said na, so phi m. So here we have some adjustment. So for the desired phase margin with the required obtained phase margin, and we'll incorporate strong additional phase lead eta. So with this equation we'll find phi m. Okay, after finding phi m, we determine the transfer function of the lead compensator. So where I have already said that we have to find alpha value. So by previous examples with the lead compensator, I have obtained the equation with this respect to phi m, alpha equal to 1 minus phi m sin phi m. So after getting alpha, now from the Bode plot, we'll determine something called, so minus 20 log 1 by alpha t. So if you substitute this here, we'll have some magnitude, right? So we are adjusting this magnitude. Okay, so we're adjusting this magnitude. Okay, so where for this magnitude I get some called frequency. Okay, that is maximum phase over frequency. Okay, so with this frequency, after getting omega m, we'll find t value. So the main thing in design we have to find here alpha value and t value. So once again just listen. After getting alpha value, already said na, in the lead compensator, this is the lead compensator. We'll just this lead compensator. We'll find alpha value. After finding alpha value, we'll just adjust this. We'll just cascade this lead compensator to the main system, and we'll find omega m value. Okay. So at what frequency this magnitude will get for the main thing? Okay. So we'll get this frequency. Okay. We'll do this. After getting this omega m value, we just substitute that omega m value, and we know alpha value, and we'll find t value. After getting t value, so now we'll got alpha value and t value. If we substitute both these things, I'll get lead compensator design. That's it. As simple as this. Okay. So after getting this, we get overall function. Now we'll find again the phase margin. If the phase margin is equal to the desired phase margin, we'll stop this design thing. If it is not meant, now what I will do is, again we'll find a new phase crossover frequency for this overall system and incorporate additional 5 degrees. Now 5 degrees now we'll incorporate 10 degrees for this overall system. Now our main system is this one, and again we'll add lead thing. Okay, this goes on properly, continuous. Okay, so we'll solve one problem now. So I came with you one problem now. So my question is, design the lead compensator GC of is equal to G of S equal to 1 4 by S plus 1 S into S plus 1 to meet the specifications: peak overshoot, settling time, and kV. Okay, so I'm asking you design the lead compensator by Bode plot, but I gave in time domain specifications. Okay, I already said that with this peak overshoot, after these calculations I got zeta value. After again I have a TS value, time domain, time settling time. So we have the equation 4 by zeta omega n. So we'll get omega n value equal to 1.54. So I obtained zeta value and omega n value. So I already said that with time and frequency correlation, I have the phase margin zeta value equal to, we substitute zeta value here, phase margin gamma equal to 53.17 degrees I obtained, and gain cos of frequency with this equation I obtained 1.19. Now my new frequency domain specifications are phase margin, which obtained here, and gain cos of frequency and kV value. Now we will design our lead compensator with these new specifications. In general, this will, if someone asks you to design frequency domain with this directly, you need not to do all this stuff. If indirectly they will ask to get you in dilemma, they may ask you like this. If directly they will give this, means there is no issue. Okay. Now let us start our journey. So this is the step 1. Step 1 is what? Determine the K value. So we are doing this. Determine the K value with the given kV value. So my kV value is 40 degrees. So we have kV equal to limit s tends to 0, s into k of g of s. Okay. So for this, after calculating this, I obtained k equal to 10 value. So my overall system. So first with this equation, I got this is k 40 by s plus t. Now we have to do Bode plot. Okay, that means up to here we just operated in region 1. Okay, in region 1 only we did this. So for this region 1, we'll find the Bode plot. So we know the procedure to do the Bode plot. This is the overall function. We'll put s equal to j omega. We'll get this thing. After this, we'll have corner frequency. So this is, don't have any corner. This part will have no corner frequency. Here we have 1 plus omega. So in denominator there is no thing. There is omega corner frequency equal to 1. Okay. Now for this, if you want to do the magnitude plot, so I give the term value and corner frequency value, slope, and 0. The term is 40 by j omega. So this is a, so there is lower frequency. So lower frequency I have this term. So I get this here. So no corner frequency, and again we have another part, this thing. We have corner frequency 1. This is origin, pole at origin minus 20 dB, and we have another G or pole thing, so minus 20 dB. So change in slope is minus 20 to minus 20. So you know already how to draw the Bode plot. Okay, I'm not going in depth. Now we have to find something called low frequency. So I have corner frequency what 1. So I keep lower frequency that is less than omega c, that is 0.1 radians per second, and high frequency omega in, which is greater, should be greater than 1. So I'm taking 10 radians per second. Okay. Now we'll find A at different frequencies. Now A at omega equal to omega L, that is A equal to what? 20 log 40 by j omega. So if you substitute that, I'll get 20 log 40 by 0.1. So I'll obtain value of 40 divided by, so 52.52 dB at omega equal to omega c. So at this omega c, again A equal to what? 20 log 40 by omega c value is 1. So I obtained 20 log 40 by 1, that is 32 dB at omega equal to omega h. A equal to what? So you know that change in slope from omega c to omega h. So what is the change in slope is minus 40. Okay, log of omega h by omega c plus omega a at omega equal to omega c. So what will have? Minus 40 into log of omega h is 10. 10 by omega c is 1 plus 32. So I obtained a value of minus 40 log 10 plus 30. So something called minus 8 dB. Okay. So I got phase magnitude values for different phases, but different frequency, that is 52 dB, 30 dB and minus 8 dB. Okay. Now we'll plot this magnitude value. Okay. So with the help of Bode plot, so I have the semi-log sheet. So I'm plotting that values. So 32 dB, 52 dB means something obtained at this value at omega equal to omega L. Okay. Now at omega c, that is omega c, and this is omega h, right? So this is my omega value varying. Okay. At omega L I got mine. So with x-axis with 0 dB, 20 dB, 40 dB, 60 dB, magnitude y-axis I kept in the left half. So 52 obtained here. At omega c I obtained 32. So this is, each division is 2. So this at here I'll have a 32 value. Okay. At omega equal to h, higher frequency, I have minus 8 value. So minus 8 value means, so 2, 4, 8, 6, this is a minus 8 value. So I'll rejoining all this stuff, I obtain the magnitude value. So this is minus 20 dB per decade, and this is overall 40 dB by decade. So from omega c to omega h, I'm having continuously minus 40. So this is a magnitude part. Okay, in exam also I have to do this thing. So okay, now we'll have with the phase thing. Here I have the phase tan inverse of the main function minus 90. So this is the main function minus 90. So initially we have minus 90 minus of tan inverse of omega value. So by this time you will know how to do this stuff, all this. Okay, if you substitute for omega value, so I'm taking minus 0.1, so it's a lower frequency 0.1, 0.5 for different values of frequencies. I got these values. Okay, so if I plot that, so for omega 1 value minus 96, that is, so in the left half, right half, I just in y-axis I gave the phase thing. So minus 60, minus 30, minus 120, minus 100. So each division is 3 units. So okay, so minus 96 means somewhere I get 10, each division is 1, so 2 after, so I keep here this value. So this is minus 96 value. Okay. At 0.5 I got minus 117 point, so that means which is 3 points less than 120. That means at point, so this is 0.2, 0.2, 0.3, 0.4, 0.5. Okay, so at 0.5 means I have a value, this will be my value. Okay, which is 1, this is my 177, right? Minus 117. Okay, now at omega equal to 1 I have minus 135. So where I'll get minus 135? So if I exclude, this is the minus 135 value. Okay, so this is minus 135. I'm not mentioning that. At 2 I have minus 153. That is, this is I have 150 minus 153. Okay, so this is the point at 2 value. So I already plotted that. So at again at 5 I have 169. This is 169, and this is at 180 minus 174. So I'm if I plot these values, I'll get something called phase values. So I draw this is called phase plot. Okay, and this is the magnitude plot. Now we have to find something called, we have to determine phase margin of uncompensated system. Okay, the third part is, so finding the phase margin of uncompensated system, right? So where we get the phase, to get the phase margin, we have to go through gain crossover frequency. So this is a gain crossover frequency where it costs 0 dB. If we go straight downwards, I obtained, this is the gain crossover frequency omega c equal to 2, 3, 4, 5, 6. Okay, so 6 radians per second is my, so gain crossover frequency 6 radians per second. At that gain crossover frequency, what is the phase crossover? So phase crossover at this gain crossover frequency I obtained. So how much part? This is 1, 2, 3, 4, 5, 6. Okay, 6 into 3 plus 150. So I obtained minus 168 degrees the phase crossover frequency. Phase at gain crossover frequency, that is 5 GC. Okay, so now we'll find phase margin, right? So if we find the phase margin, so what I'll get 180 plus minus of 168, I obtained something called 180 minus 168, so I had 12 degrees. Now our point is, so for this, even though we incorporate the in region 1 with the given k value, after finding this phase crossover frequency and phase, we got the phase margin equal to what? 12 degrees. Okay, phase margin equal to 12 degrees. But our requirement is something called 53.17. That means only we operated region 1. Now we have to operate the region 2 by adding what? Lead compensator. That is the main point. So involving adding the lead compensator means what we have to find? We have to find maximum phase angle, right? So this is called a maximum phase angle. So how we'll find the maximum phase angle? So this is the equation we have on maximum phase angle. This is the desired phase margin, and this is obtained phase margin, and this additional phase lead to be added. So we have 5 degrees. This is what 53.17. We obtained what 12 here. So if we substitute that, I get 53.17 minus 12 plus 5. So I obtained something called 46.17 degrees. So this is a phase angle. Okay. Now what we'll have with this, we'll find alpha value. Okay. So we'll find alpha value. So we'll find alpha value 1 minus sine of, so 46.17 divided by 1 plus sine of 46.17. So after finding that, I obtained a value of, so this is a lot of, not lot of math involved, only is a simple idea. Okay. So I obtained something called 0.1618. I already know that alpha value should be less than 1. So I obtained the reasonable value. Okay. So what I said I get, so the dB magnitude at omega m. No. So we'll get phase, maximum phase angle. So initially we'll use phase, maximum phase angle, where we obtained means at maximum frequency. So how we'll get the maximum frequency value means we have to find the dB magnitude. So dB magnitude at omega m. So what is that means? This is the magnitude, right? So if you go to back calculations, so that lead compensator, so this is the omega m, this is the dB magnitude, right? So we have to find the dB magnitude. So this is minus 20. So if you find log of 1 by root alpha 0.1618 value, so I obtained minus 10 log so something called minus 7.8. I get approximately, I'll take minus 8 dB, right? So minus 8 dB I got. So I got minus 8 dB. So from the Bode plot of uncompensated system, the frequency omega m corresponded to 20 dB. So if you see carefully, we just adjusted plus 20 dB plus 20 log 1 minus 2 to minus 20. That means we are moving our lead compensator to above. Okay. So we have something called lead compensator here. So we'll have a lead compensator here. So we are improving we'll improve for this main system that region 1 we'll adding something. Okay. So that means, so we are getting minus 80 dB value. So where is that value 8 dB? So already we find it. So here the 8 dB value here. So that frequency is called omega m. Okay, I said that. So here omega m equal to 10 radians per second. Okay. So we find omega m value, right? So after getting omega m value, so from the Bode plot of uncompensated system, the frequency omega m correspond to dB gain of minus 8 dB. We found to be omega m value equal to 10 radians per second. Okay. After getting this 10 value, we'll find this t value. So how we'll find? So omega m value is 10 and angle is 0.1618. So I obtained something called t value 0.248. So if we substitute that, we'll have this transfer function gc of s equal to s plus, so this is t value, so 1 by t means, so I have 4 s plus 1 divided by 0.1618 into, so 0. So and t value is what again? So t value is 0.248. So I got 24.92. Okay. So this is my, so the whole ZC value equal to 4 and PC equal to, so 24.92. So this is a lead compensator I obtained. So I am a pole R is in 0 at -4 and pole at some far away. So see, if you observe carefully, this is almost far. Okay, so that is 24.92. But for lag, will be different. We'll observe shortly. So so we have the reason for this thing to type all in this format. That is, we'll obtain the overall compensated system 0.1618 1 plus, so t value 0.248 t divided by 1 plus 0.248 into t values, alpha will 0.1618 into t value 0.248, so 0.04s. Okay, so we find a controller, so we incorporate this. So there is a thing called, so there the compensator will provide so this compensator will provide an attenuation factor alpha. Okay, to nullify that alpha, compensator will give, this is an amplifier, so we'll give amplification for this to nullify that attenuation factor in add series. So after incorporating this, 1 by alpha and alpha will get cancelled, and the overall system will be this one, that is 1 plus st by 1 plus s alpha t into gc of s. Now our job is to find the Bode plot for this thing, that is g naught of s equal to 1 plus, so s by t, so s plus, so 1 by t value is s by, so this is 1 plus st form, so 1 by t value is 0.4 by 1 plus s play, so alpha 1 by alpha t to get in the frequency form, so I'll get 24.92, so into, so gc of s is the value of what, so I have 40 into, so 40 by s into s plus 1. So our job is to find the frequency domain Bode plot for this to find verification. Okay, now we have to do verification for this, so that is 1 plus s by 4, that is 1 plus s by 24.92 into 40 by s into 1 plus s. So instead of 24.9, shall I take approximately 30 degree? Yes, I can. So I'm not, so I can take, this is 30, I'm taking 30, so no ambiguity should be there. So now corner frequency for this whole thing to done, so the corner frequency omega 1 is 1, so from this I'm having omega equal to 1, omega c2 is 0 is added 4, and omega c3 is 30. Okay, now we draw our Bode plot by doing magnitude and phases. So the magnitude term is 40 by, so we'll initially put s equal to j omega, we not forgot that, 1 plus j omega by 4, 1 plus j omega by 30, 40 by j omega into 1 plus j omega. So from this we get corner frequency. The first part is this thing. Use further. So have patience, guys. This, if you work out, you will. The first part is this one. So this is our first part, that is term 40 by j omega. The corner frequency, there is no corner frequency, and the slope is for this minus 20. So there is no change in slope. The second part is 1 by, so next corner frequency is omega c1 equal to 1, that is 1 by j omega. For this I'll have a slot minus 90. Now again at omega c2 I added 0, that is 1 plus j omega by 4. So that slope is plus 20. Now again I have a 0, so pole at 1 plus j omega by 30. Okay, so this is term 1, term 2, term 3, term 4. Okay, so I'm having corner frequency omega c3, so omega c2 is 4, omega c3 is 30. So here 0, this is 0, that's why I added plus 20. Here pole, that's why I minus 20. Now we'll see the change of slope. Up to certain value there will be no change of slope. At corner frequency omega we have a change of slope, that is minus 20, that is minus 40. Now again up to certain value there is no change. Up to that corner frequency there will be a change, that is minus 40 plus 20, that is minus 20. Again up to certain values there is no change. At corner frequency omega is 3 we will have change. So this change of magnitude slope will get to infinite frequency. Okay, so I'll continue this. So here I'll take so lower corner frequency which is less than omega c1, that is 0.1, and higher corner frequency which is greater than omega c3, that is 100. Okay, so I'll plotting that omega at omega L equal to A equal to 20 log 40 by first point. So 20 log at a frequency 0.1 I got 52. Up to certain value there is no change in phase. Plot at 2 output omega c1, right, 20 log 40 by 1 I got 32. After that omega c1 again has a change in slope, that is minus 40. With the change is minus 40 with respect to 4 by 1 plus addition of this magnitude I'll get 80. See, this goes continuous, again you have minus 20. So I obtained a different magnitudes for so obtain different magnitudes omega lower 32 minus 8. Okay, so now after getting the magnitude values, we'll do what phase plots. Okay, so phase plot. Now how do they? So this is the main function. So initially this initial term, at first term we have minus 90 degrees. So minus of omega c1 we have pole at 1, so minus tan inverse of omega, and again we have this term involving omega c2. So I have, this is in the numerator, I'll have plus tan inverse of omega by 4, and again I having at omega c3 this thing term denominator, so minus tan inverse of omega by 30. Okay, if you substitute different values of omega, I have obtained these phases values. Now we'll plot the Bode plot for compensated system. So this is our compensated system obtained. Okay, system, and check the phase margin. Okay, so my phase margin should be greater than 53 point. So not exactly 53, but it's not less than 53. So 53.17 given phase margin. So if it is exactly 53 means exact, it would not be possible, but my phase margin should be greater than this. Now let us check that by plotting the phase margin. So this is a compensated system. So at omega 1 value, so obtained 53, so 52, and at omega equal to omega c1, at omega 1 I will obtained 32. I plotted this, and omega c2, that is at 4. So this is a 2, 3, 4. Okay. So obtained value of 8 dB. So I plotted here. This is the 8 dB line. Okay. And at omega is c3 at 30. So obtained minus 9.5. So this is a minus 9.5 value. Okay. And at omega 10, 100, higher bound frequency, I got minus 30.5. So this is minus 30.5. So between minus 20 minus 1, this is so the magnitude plot for compensated system will be something like this. So this is a magnitude plot. So this is minus 20. So minus 40. So minus 20. Why here got minus 20? Because 0 is added here. That is, at this reason only we included lead compensator. And we have minus 40 dB by decade. Okay, dB by decade. Now we'll plot the phase thing. So at omega 1 I have minus 94. So at light side I take minus 60, minus 90, minus 180, and minus 150. So minus 94 at this point. Minus 94 means at this I bought at this point. So already plotted those values. At 0.5 I got minus 110. So in between this thing I'll have this minus 110, minus 90. At minus 90 to minus 120 I'll have approximately at this point. And at 1 I have minus 122. That is for after this minus 120 I'll get minus 122. This one, each division is 3. You have to mention. Okay, each division is 3. And at 2 I got minus 130. That is up here. Now we are having a lead compensator. So here observe the phase margin is getting, the phase plot is getting something called reverted. Okay, at 4, at 5 I get minus 126. At 10 I got minus 124. And again the lead thing is relieved, and we got at higher frequency at value of minus 164. Now if I plot this, I'll get phase plot. Okay. Now our job is to find phase margin, right? So at gain crossover frequency, so this is a new gain crossover frequency. So we'll name it as omega GC. So what is what? 5, 6, 7, 9. So 9 radians per second. At this gain crossover frequency, new gain crossover. So new gain crossover. I get new phase, right? So I got something called 5GC equal to minus 1. So 1. So let us say minus 124, right? So this is 123. In between this we have some. So approximately minus 124. Minus 124 is a new phase at new gain crossover frequency. Now what is the phase margin is 180 plus 5 new gain crossover frequency, get 180 minus 124. I obtained what? So 56. So that is greater than 53.4. So my design is accepted. Okay. So if this is not accepted means now we'll have to continue from second, fourth part. So we have to additionally incorporated 5 degrees. Okay. So once go through this slightly, what we have built here is nothing big one. So this is my compensated. So this is my uncompensated system. Okay, where I In first region I got with the given KV value, I got K value, I got border plot. After finding this phase margin, I didn't got much phase margin improvement. Now I've included the phase margin, the lead compensator, and I got new gain cos of frequency and all this stuff, and the phase margin is length. Okay, so follow these steps so you'll get the clarity. So thank you guys. So we'll see the next class of lag compensator. Thank you guys.